This week we're covering flow in pipes. And essentially there's two main components to this topic. There's laminar flow and there's turbulent flow. On the video we talked about laminar flow, which is a flow regime where viscous forces dominate. And if this viscous forces dominate, we have several properties. For example, the streamlines are well defined. And for some control conditions, it's easy to find exact solutions to the Navier-Stokes equations that give us that velocity profile for that laminar flow. When we finished that exercise, or when we finished the class, we actually were working towards coming up with an equation for laminar flow in a pipe. And I can't go over the whole thing just because we've already covered it before, but essentially we had a pressure-driven flow in a pipe where because of the pressure variation in the longitudinal direction, we know that the velocity profile will look something like a parabolic shape or something similar. We wanted to make this equation very generic, so we just gave this pipe an inclination theta. And that inclination is so that we can find a component for our body force vector, which in this case, we can just treat it as the gravity vector. We said that the pipe had a radius r, and we tried to solve this equation in cylindrical coordinates with a longitudinal component x, a radial component r, and an angular component theta. I think that was most of the information given, or all the information given for this particular project. We had a pressure gradient, so we did have some pressure gradient that was driving flow. And we decided to solve this problem by writing down the Navier-Stokes equations in their cylindrical form. Now, as a recap, let's recall that the Navier-Stokes equations consist of the acceleration term, the pressure gradient, the viscous term, and the body force term. Now, writing these in cylindrical coordinates, I'm just going to write this down here. We had in cylindrical coordinates that the x direction component of the Navier-Stokes equations looks something like this. We had our expansion of the material derivative in cylindrical coordinates, where I'm just going to call the longitudinal component velocity v sub x. I'm going to call the radial component of velocity v sub r. And I'm going to call the angular component of velocity v sub theta. And the only reason I'm writing down this equation is because I do want you to see that when you convert your Cartesian coordinates into cylindrical terms, there are some factors that you're going to end up with when you do your conversion. If you don't remember how to convert Cartesian coordinates to cylindrical coordinates, it's actually not that complicated, but we don't have time to cover it in class. But just recall, for example, if you're going to convert Cartesian to polar coordinates, x is just r sine theta, r cosine theta, y is just r sine theta. So the same thing applies for cylindrical coordinates, except that here, in addition to your x's and your y's and your r's and your thetas, we're looking at derivatives as well. So that's where all these extra terms are coming from. Now, I mentioned in class yesterday that because we are a little bit short on time because of, we fell behind on the material, we don't really have time to go over the cylindrical coordinate transformation. So instead, I wanted students to focus on what these terms mean. So not necessarily where they come from, but at least we should try to understand what they mean so we know how to solve them, how to solve this Navier-Stokes equation in order to find the velocity for this flow in a pipe. And one final question you may have is, why are we doing cylindrical coordinates? Why not Cartesian coordinates? We're looking at Cartesian coordinates. Flow varies in the with the y and z direction as well. And I would say just good luck trying to solve that equation. This is going to be really, really, really hard. So that's why we use cylindrical coordinates instead. Now, the reason I'm writing this, I just want you to see where these terms are coming from. This is the change in velocity along the longitudinal direction x with respect to time. Steady system, so we can neglect it. This is the radial velocity. Radial velocity is any velocity component that moves away from the center. Now, we deduced that because this was laminar flow using continuity equation, there is no radial component of velocity, so 0. This is the angular velocity. That is the velocity along the angular direction. And we found because there is no spin, there's no vorticity in this flow, this term also goes to 0. And then we know that this is an infinitely long pipe. There is no change in velocity along the longitudinal direction, so this term went to 0. We do have a pressure term. We do have a change in velocity along the radial direction, so we do have this. We don't have any change in velocity in the angular direction because this is a symmetrical system, right? So the velocity, if you're at some distance from the center, it doesn't matter where in the pipe you are. If you are at the same distance from the center, your velocity won't change. Does that make sense? Notice that the velocity of the walls is 0, and then it kind of starts to increase parabolically until it reaches the velocity at the center. So it doesn't matter where on the axis you are, right, on the angular axis. As long as you know your distance from the center, that's really the only thing that determines your velocity. So that's why this term was 0. And again, no variation along the longitudinal direction. And this was simply gamma or negative gamma dh over dx. Our pressure term, we found that it was an ordinary or total derivative, dp over dx. And after solving this equation, again, the solution is on the video I uploaded. I just wanted to make sure we know where these terms are coming from. But after solving this equation, in class, we ended up with the following equation. We ended up with an equation 1 over r times the derivative with respect to r. And even though we're writing partial, these are actually total derivatives because we know that velocity only changes with respect to r in this case. So derivative with respect to r of r times the derivative of the velocity with respect to r, and all this was equal to a constant lambda. And in this case, the constant lambda was actually the same constant that we found for our flow between parallel plates. So in this case, we got this equation where lambda was actually equal to 1 over viscosity d of pressure plus gamma h over dx, which is a constant. Okay, so that's where we left off on our last class. Again, if you want to know how we go from here to here, you can look at the last class. I think the steps were pretty detailed. But then I do want to finish here, right? I don't want to leave this like this, right? We still need to solve for the equation, right? So what we're looking for, right? What we're looking for is an expression of Vx as a function of my radial distance r. That is the distance from the center of the pipe. That's what I want. For boundary conditions, we know that the velocity at the walls of the pipe is 0. Do we agree? Okay. So we can say that the velocity Vx at a distance capital R, which is the radius of the pipe, is 0. However, we still need another boundary condition. And I mentioned that we're going to have to do a little bit of deduction here to figure out, just based on the information that's given to us, how to write down another boundary condition. So there's two options I think we can take. The one that we took in class was to look at this velocity profile. If you know that the flow in the pipe, the friction really only comes from the pipe walls, where is the highest velocity in this pipe, Josh?
At the lowest point.
Let me try again. Remember, it's a pipe, right? So friction is everywhere.
Oh, in the center.
There we go, in the center, right? So we know that the highest velocity is in the center. So one way to write down this boundary condition is to say that Vx, when radial distance equals 0, that's the center, is my maximum velocity. But that doesn't really help me because we don't know what that maximum velocity is. So perhaps another way to write it down is to say that the derivative of Vx with respect to r at a distance of 0, what's the derivative of a function at its maximum or minimum point? 0. Okay, so I think this is a better boundary condition to have, right? The derivative of Vx with respect to r at 0 equals 0. So now that we have our boundary conditions, let's try to solve this. There's still a little bit more integration we need to do. We want to solve for Vx in terms of r. What's the next step here?
Give it r dv dr.
All right, cool. So we get, I'm going to try to write down as many steps as I can, as long as we have time, right? But we can say that d over dr of r dvx dr is equal to lambda r. Is that correct? Do we agree with that? Okay, good. Then we can move dr to the other side and integrate, right? So if we integrate this equation, we get that r times dvx dr is equal to the integral of a constant times r with respect to r. What does that integral equal to? Integral of lambda r dr?
1 over 2 r squared.
lambda over 2 r squared, right? Plus a constant. That's correct. I'm going to call it a. Good. So we have a constant. This is a constant of integration. It's an unknown value. We don't know it yet. But there's still a little bit more to solve, right? We still need to find that Vx. So what else can we do now? Divide by r. Okay, so we get dVx over dr equals lambda over 2r, right? R squared over r is just r, plus alpha over, a over r. And now we can multiply by dr and then integrate, right? So we integrate this equation, we get that Vx equals the integral of lambda over 2r would be lambda over 4r squared. We know that. What's the integral of a over r with respect to r?
It's like natural log.
Natural log, right? Plus the natural log. Plus a times the natural log of r. Can't forget that constant. What am I missing? Another constant, right? I'm going to call it b. I know everybody wants to call their constant c. I just like to use a, b, c, d, d, in that order, okay? Good, so we have this equation. We have two unknown values. We need to find these two unknown values. How do we find those values? By applying boundary conditions. Good. So I want to start with this one because this one's the ugliest one. You look at this expression. This looks pretty manageable. This looks kind of ugly. Like, ugh, how's that going to look like? So let's start by trying to find a. Now, if we apply the condition Vx of capital R equals 0, capital R, doesn't really give us anything because we still have two unknowns, a and b. So we can't do that. However, we can try either one of these two boundary conditions, and with either one, we should get a value for a. So let's start in order. Okay, let's try it with our first or our second boundary condition. The velocity at 0 is Vmax. Now, we don't know what Vmax is, but we know that it's a number, right? It has to be a real number because it needs to exist in this physical space. So it is a real number, okay? So we get that the velocity at 0 is Vmax. So I can say that Vmax, that's the velocity at 0, equals lambda over 4, 0 squared. Okay, nothing. A times natural log of 0 plus b. And now my question is, what's the natural log of 0? Think. What does natural log mean? What? All right, remember, natural log is e elevated to the power of something gives this. So e elevated to the power of what gives 0? E to the power of 1 is just e. Nothing, right? There is no solution. This is undefined, but this is a real number. So if this is undefined, but this is a real number, then what can I do here? What does a have to be equal in order for this to not be an undefined number? Say it? 0, right? Okay, so we get from this boundary condition that a has to be 0 because this cannot be part of the equation. If this were part of the equation, then we will have an undefined velocity at the center, but we know that the velocity at the center has to be a real number, right? It's a real physical space. Now, if this isn't convincing enough for you, or if you feel that you need to make a couple of jumps and assumptions to get here, let's try another boundary condition. Let's try dvx dr equals 0. All right, dvx dr of 0 equals 0. So let's try that first, okay? So if I do d of velocity with respect to r, what's the derivative of velocity with respect to r? Well, the derivative of this is lambda times 2 over 4, so that's lambda over 2 times r, plus, what's the derivative of natural logarithm of r? It's just 1 over r, right? So plus alpha over r, and then the derivative of b is just nothing, 0, because b is a constant. And we know that when r equals 0, this equals 0. So we get 0 equals, r equals 0, so this is 0, plus a over 0. What is a over 0? Undefined as well. we can maybe take a limit. We can say, okay, as r tends towards 0, this tends towards infinity. We could. However, that doesn't really help us because the answer still has to be 0. So if this has to be 0, what does a have to be in order for this to be 0? 0. So what we get from here is that there cannot be a natural logarithm term in our equation because it doesn't make sense physically, right? Physically, this says that at the center of the pipe, we have an undefined value of velocity. Physically, we know that we need to have some velocity at the center of the pipe, right? You don't have flow all the way to the center and then suddenly the water disappears, okay? So we get that a equals 0. And then my equation becomes v of x equals lambda over 4 r squared. A is 0, so plus my constant b. And then we still need to find b. Go ahead.
Isn't 0 over 0 still undefined?
It's undefined, right? So remember, this is the derivative, right? This is undefined, so this cannot be a part of the equation. So when we say a equals 0, all we're saying is this term has no bearing on the equation. So remember one thing, the physical equation is this one, okay?
But if a was 0, wouldn't the equation still be undefined?
Well, here's what I'm saying. The physical equation is this equation, right? Not this equation. This is just a derivative. It's just a mathematical derivative. Exactly. Yeah, so here, this is where we're applying that 0, right? Because the 0 just means that there is no term, okay? So that's a really good question, right? We do need to keep in mind that the physical equation is the velocity equation. The derivative is just a mathematical thing, okay? You can say, yeah, derivative of velocity is acceleration and with respect to time, so, and that is a physical property. But this is a velocity gradient. Sorry, this is a velocity gradient, and that's simply a mathematical expression, okay? It's supposed to try to represent physical reality, but this is really the physical equation here, okay? Really, really good question. So we can find this b, and I'm going to try to run quickly so that we can solve other types of flow. But we can find this b by applying my other boundary condition at r vx equals 0. So 0 equals lambda over 4 capital R squared plus b. This gives us that b equals negative lambda over 4 capital R squared. And I think from here we can pretty much solve this equation, right? We get Vx equals lambda over 4 little r squared plus b, so minus lambda over 4 big R squared. I can factor out my lambda over 4. And I get this equation. Now, does that make sense? I think it does. When my little r, when my radial distance is equal to the radius of the pipe, capital R, this becomes 0. And it's true because the velocity at the walls of the pipe is 0. When my radial distance is 0, this has its maximum value, right? Because the highest value we get is when this is equal to 0. Let's plug in that value for lambda so we can get the final, the latest and greatest, right, equation. So lambda is 1 over mu times the pressure and gravity gradients. So I'm just going to say 1 over 4 times mu times dp plus gamma h over dx. And all this multiplied by r squared minus the radius of the pipe squared. And we get a pretty nice, easy to use equation, pretty much starting from Navier-Stokes. And yeah, it's something pretty solvable. Any questions? Yeah.
So in your final equation, you don't have any theta in there, so would that mean that the angle really doesn't matter?
Are you referring to this theta?
Yeah.
So this theta, and this is something that I skipped, but we covered in the last video. This theta, right, is related to your drop h and your distance x through this dh dx. So that's where the theta comes into play. Normally, we try not to express it in terms of theta. We try to express it in terms of pressure drop. Yep. Any other questions? Good. You may think, wait a minute, when r equals 0, you get a negative value. But remember that the pressure gradient is negative as well. Okay? So you get negative times negative, you're still going to get a positive velocity. So don't be thrown off by the fact that you'll get a negative value at the center of the pipe, because you have a negative value here, but this dp over dx is also negative, okay? So that was what I wanted to finish covering on Tuesday. That's laminar flow, where viscous forces dominate. We can do some other exercise. I can ask you, based on this, what's the maximum velocity? What's the shear stress on the pipe? We can do a lot of those things. But why cover it in class when we can cover it during the take-home exam? So instead, let's move on to turbulent flow. So we said that when we're dealing with laminar flow such as this one, the viscous forces dominate this flow. My viscosity dominates the flow. However, when my inertial forces dominate the flow, I have turbulent flow. So we already dealt with laminar flow, where the viscous forces dominate. But now we're going to look at turbulent flow, where the inertial forces dominate. We mentioned on our last class that we can find laminar and turbulent flows by using a dimensionless parameter called the Reynolds number. And this Reynolds number, I don't want you to take these values and memorize them, because different flows, different fluids in different environments will have different ranges. What we need to know is that when the Reynolds number is very large, my flow is turbulent. And when it's very small, my flow is laminar. Some sources will say that laminar, you can have laminar flow all the way up to like 9,000 if it's very well controlled, no external forces acting on it. So take these numbers with a grain of salt, because different books, different situations, different scenarios, different lab environments will give you different ranges. What you do need to know is that if this number is very big, and when I say very big, think bigger than 10,000, right? When it's very big, it's turbulent. And when it's very small, and when I say very small, think something like less than 1,000, right? And in the range of hundreds or tens or something, it's laminar. There is a region called the transition regime, which is in between, where the fluid can behave like both, but we're not going to cover that here. Now, turbulent flow is an interesting beast in and of itself. It's so interesting that we're going to simplify it so much in this class that I don't even think you can say that you know turbulent flow or that you've studied turbulent flow, because we're going to simplify it so much that it's going to lose everything that makes it interesting. But we have to, because nobody really understands turbulent flow. It's a really complex phenomenon. I mentioned last week when I was talking about the history of fluid mechanics that ancient civilizations looked at turbulence as the enemy, right? The chaos monster, because we cannot understand it. We cannot deduce its patterns. We cannot predict it. So turbulent flow is flow where inertial forces dominate. And essentially, I'm not going to say it's unpredictable, but it is very hard to predict, because turbulent flow is essentially a flow that functions as a chaotic system. Does anybody know what chaos means in terms of physics? It seems like random, like perceived randomness, right? A chaotic system is a system where a tiny, like you can say as tiny as you can, a tiny change in the initial conditions is going to make a big change in the final conditions. Now, what that means is that it's really hard to predict. So, for example, you can have your initial conditions, run these through some calculation, and then get your final conditions. And on normal systems, not chaotic systems, but on ordered systems, if you make a change in the initial conditions, you're going to get a change in the final conditions. If you increase that change in the initial conditions, you'll increase the change in the final condition. That's pretty much any equation that's ordered, right? You have the equation y equals x squared. If you increase your x, then you're going to increase your y, right? In chaotic systems, if you make a tiny change, really, really small change in initial conditions, you're going to get something completely unexpected in final conditions, right? So the changes that you see don't really match the range of changes that you apply. And fluids are really, really hard to predict because of this. And because when you are studying fluids, think, is it possible to consider every single thing acting on fluid? Think of hurricanes, right? When we're trying to predict hurricanes, what factors, what environmental factors or physical factors do we need to consider in order to study the wind particles in a hurricane? Let's see, we need the density of water, but you know that the water is not just pure, distilled water that's being rained down on us, right? We need the temperature, the density of air, the pressure of the air at that movement. The pressure is influenced by the velocity, but wait, we want to calculate the velocity, but we need the pressure, which itself depends on velocity. There's so much, right, that we have to consider that's why you see the hurricane predictions. They look like these cones, right? That doesn't mean that the hurricane is going to grow into a cone. It means that our hurricane can be anywhere inside the cone as it travels through its trajectory, right? Now, I like the hurricane example because we have this cone, and the cone means that if a hurricane is here, as it travels in this seemingly, kind of like defined trajectory, it can be anywhere inside the cone. And here's where we can start to study turbulent flows. We don't know exactly where the hurricane will be, but we do know that if we take all of the possibilities of where the hurricane will be and average them, we get this trajectory. Does that make sense? That's how we find the trajectory. We find all the possibilities of where it can be. When we're not sure where exactly it can be, but if we average all these possibilities, we get a pretty well-defined trajectory. And for the most part, these trajectories are, pretty much accurate. I mean, there's some cases where they just completely changes trajectory, but for the most part, the trajectories are accurate. And that's the type of analysis that we're going to do in this class. Because this is an introductory class, our analysis will look at averaged values. We can average our values such as our velocity field, our pressure field, even our density fields for compressible flows. We can average them over time. We can average them over a depth. We can essentially, when I say we're averaging our values, it means we can't really calculate every single velocity, right, of a fluid particle with precision, but we can at least find a trend of where the particles are moving. One example. Let's say you have flow inside a pipe, just like what we calculated earlier, but this time the flow is turbulent. You use maybe a pump or some other device to increase the pressure here so that it's higher than the pressure here. The pressure here is higher. So you're applying two pressures. This one is higher. In which direction would the fluid move? Yeah. However, if my flow is turbulent, I can't say that my fluid particle is moving in a straight line, right? If my flow is turbulent, that fluid particle is moving in pretty much what's an undecipherable path, where there's a lot of mixing involved. Particles different particles can mix with each other. Its density may change as it moves. It's a really, really unpredictable path of particles. So I'm not going to try to undertake the task of predicting the movement of these particles individually, but I can say with certainty, regardless of how these particles are moving inside the pipe, what we do know is that every single particle that was here with enough time is going to end up here. Is that correct? Can we say that? Right? We can. So what I'm going to do is I'm going to stop caring about finding the exact movement of the particle and instead focus on the movement of the group of fluid particles as a whole. Okay, so I'm going to say all these particles that started here, it doesn't matter if they're moving erratically. I know that at some point, somewhere in the future, they're going to end up here. They're not going to end up at the same time. Some of them will go first, others will go later, but at some point, they're going to end up here. So what we're going to do is we're going to average the velocities of these particles throughout this pipe and throughout time to say that essentially our system is equivalent to a laminar or defined system where particles are moving along the direction of the pipe with a velocity of V average, where V average is the average velocity of the particle throughout its trajectory. So even though we can't calculate the particle's movement at every single point in time, at every single point in space, we can at least try to calculate the average velocity. And how do we know that? If you have a pipe, and this is just a quick example, right? You have flow coming out of a pipe. Well, one easy thing to do is to figure out how much volume the pipe is, the pipe is transporting, how much volume, and how much time it takes. You get volume over time, you get flow rate. You divide it by the area, you get average velocity. So doing something very simple, not really mathematical, you can find this average velocity. And that allows me to but not have to worry about this erratic movement by dealing with average values. So what we're going to do here is we are going to study turbulent flows under the context of averaged velocity values. And like I promised last week, we do want to start dealing with more practical applications. So let's start to now look at most pipe systems which you will see in industry, which are turbulent flow systems. In order to study these turbulent flow systems, instead of focusing on mass and momentum as we did with the Navier-Stokes equations, let's focus now on energy. And I'd like for you to recall the energy equation, which we studied several weeks ago. You may remember that energy equation looks something like this, right? We're not really focusing on mass and momentum this time because we cannot calculate this movement. So instead, we're looking at average values, and those average values will be studied by looking at the law of conservation of energy. So this was the energy equation, right? Now the energy equation is it expresses the law of conservation of energy, so it is a law, right? It should apply to any system. In this case, this is a case of steady uniform flow. And what we can say is, if my average velocity in the pipe is steady, then I can treat it as steady and uniform. Because in this energy equation, this velocity term will actually be an average velocity term, and we should still get correct results. They're not going to be exact and precise to the dot, but they'll still be applicable for our work. And that's really what we want to lead you to study, right? Our work. Now, when we studied the energy equation, we mentioned that we have our energy terms: pressure, kinetic, potential. We had pump head, which was energy added to a system. We had turbine head, which was energy removed from a system. And we have this HL term. Do you remember what this HL term was? Head loss, right? And head losses were energy that was lost through heat transfer, friction, and other changes in energy. So when we study this turbulent flow in pipes, our focus will be on these head losses. Because you'll see that as we study turbulent flow, these head losses will determine pretty much how this flow behaves, or how this equation pretty much behaves. Now, these head losses are going to be pretty much the focus of our discussion on turbulent flow in pipes. So let's talk a little bit about them. Remember that flow rate is simply average velocity times area, because we are going to be dealing with average terms. And we know that head loss is any loss in energy that a system undergoes. Because head loss depends on things like friction, heat transfer, do you think the head loss will be greater or smaller with increasing velocity? So if my velocity is greater, do we have more loss or less loss? More, right? Because if you have more velocity, you have more friction force, right? More heat transfer. Like rub your hands slowly and then rub them faster. Which one generates more heat? The faster movement, right? So that means that our head losses, what we know so far is that they're going to be proportional to the velocity. Remember, these are head terms, right? They're length terms. So our velocity has to appropriately be a head term. So our head losses will be proportional to our velocity head. In most applications, we are going to split the head loss into two terms. And in order to define those two terms, I would just like for you to try to think conceptually, what causes a loss in energy? Well, I already talked about friction, right? We talked about that a lot. And in fact, that is one of these terms, friction. But what else causes a loss in energy? What do you think? If you have flow in a pipe system? Well, gravity is included in the potential term. So what else? Sorry? What? Come on, man. This is too advanced. Let's go back to like, what? Okay, let me rephrase that. What causes loss in a system that could be studied by undergraduate fluid mechanics students? Direction changes, right? Any changes in direction, right? Any changes in geometry, right? Any changes in pretty much anything, temperature, any changes in the system. And all those changes are called component or minor losses. Friction loss sometimes is called major loss, but you'll see that we call it friction loss more than major loss. So these are the two types of losses that we're going to study, and we know that both of these are proportional to the velocity head. Friction loss can be quantified by an equation called the Darcy Weisbach equation. When you're in civil engineering and when you're in the business, not just civil but also mechanical, when you design pipe systems, pressurized pipe systems, you'll see that there are two main equations that you use in the field: Darcy-Weisbach equation and Hasten-Williams equation. Hasten-Williams equation has a little bit more pull. It's used a little bit more by engineers. So I'm going to teach you Darcy-Weisbach equation because that is the one that most people in research, like most textbooks, try to push. But you'll see two equations, Darcy-Weisbach and Hasten-Williams, when you are in the field working in pipe systems. Now, the Darcy-Weisbach equation, which is the one that we're going to focus on for this class, looks at the elements of this system that cause friction and then relates them, right, to the velocity head. We know that head loss is proportional to the velocity head. And instead of just giving you the equation, let's try to come up with the equation ourselves. First off, this is the length, this is the length, which means that any coefficient that you multiply this has to be a dimensionless number. So we need to keep that in mind. So let's look at this pipe. You have flow traveling from here to here. Remember, we're looking at average flow, but pretty much travels from here to here. What of this pipe contributes to the amount of friction that it experiences? What type of area? Okay. I like that, right? Diameter, right? Yeah, you're both referring to the same thing, right? So we know that the diameter of the pipe will affect the friction. I have a question. Would a bigger diameter result in more friction? Does a bigger diameter, a big diameter, mean more friction? So we always have this discussion. Half of the students say no, half of the students say yes. Who said no? Why?
Because the friction on the contact, wouldn't it be the same?
Okay, who said yes?
Regardless of the size?
All right, why?
Well, because there's more, like because there's more surface area for the water or whatever the fluid is to be in contact with.
All right, so Hemang, you're saying that no, because there's more free space. Is that what you said? More. Okay, there's more free liquid that's not in contact with it. But you say yes because more area actually means more liquid in contact with.
Right, so for friction loss necessarily wouldn't, I don't know if that would change, but there would be more friction, right? That's a lot.
All right, so who's right?
We're both right.
That's not true. On a smaller pipe? I like that you're thinking in terms of velocity, but let's not look at that now. Let's focus only on geometry. So that is a really good point that you're bringing, but let's try to focus only on the geometry because the velocity is already included here. So let's just focus on geometry. What do you think?
Are you comparing if they have the same flow?
Yeah, let's say the same velocity because this term we want to keep this constant. Let's say we have the same velocity. So let's not really focus on any effects on changes in velocity.
If you had this the smaller pipe in direct relationship to the bigger pipe,
the bigger pipe would technically allow the same flow, but it would have more friction loss. But the smaller pipe, actually no, the smaller pipes in total fluid would have more friction affecting the cross-sectional area because the distance from the edge. Yes, but the bigger pipe does have more surface area, so I'm going with that one.
You had the right answer, and then you said, but I'm going to go with the wrong one.
It goes against my intuition.
All right. Good job. I think you're the only student that actually answered it right and that said, but. No, you're all right, okay? I mean, you're not all right. Most of you were wrong. But you two are right. The bigger the diameter, even though we technically have more portion of the fluid in contact with the pipe, as a percentage of the amount of fluid, it's actually less because you have more free fluid flowing. Remember that friction affects the fluid based on its distance from the center, or from the wall. So the more fluid or the more free distance you have away from the wall, the less friction you're going to have on this fluid, the easier it will flow, the less friction loss. I have this discussion every semester with my students because I think it's a good one, because it's kind of intuitive, but not really, and you can kind of come up with a good argument for both.
So does that mean that like friction in like total friction less, but with friction at the pipe level would be more, or is that still not correct?
That's still not correct. Yeah. So my point in saying all this is we mentioned diameter, and we mentioned that with a bigger radius or with a bigger diameter, we have less friction. So how would you write down the diameter here?
In the denominator?
Denominator, right? Okay. So we have the diameter in the denominator. Good. Good job. I like these conversations. I feel sad that we're sacrificing problem time, but I think this is a little bit more rewarding for me because you can always do your homework on your own. What else causes friction?
The roughness of material.
The material, right? Now, I'm not going to come up with another 20-minute conversation. Let's just say that the material can be all jumbled into a coefficient that we're going to call the fanning friction factor, or F. Okay? What else determines the amount of friction?
How long the pipe is.
The length of the pipe. With a longer pipe, do we have more friction or less friction? More. So where does length go? Good. And there you have it. You have almost single-handedly come up with the Darcy Weisbach equation. Congratulate yourselves. Pat yourselves in the back. This is the equation that we're going to use to determine friction in this class. In industry, like I said, there's another equation called the Hasten-Williams equation, and we can always talk about it maybe during the review session. But for this class, we're going to focus on the Darcy-Weisbach equation. That's how we calculate friction losses. Now let's try to solve an example. This is not going to be a complete example. We're just going to simplify it as much as we can, just so that we can get some practice with these new terms, because I know we're dealing with some new terms in here. Okay? Let's say we have a horizontal pipe. This is a horizontal pipe. And let's say that we have a flow rate of 0.1 cubic feet per second. Traveling throughout the pipe. The pipe has a length of 1,500 feet, very long pipe, and a diameter of 1.5 inches. Just based on these numbers, do you think the amount of friction will be relatively high or relatively low? Relatively high, right? Small diameter, long pipe. Good. The pipe is carrying water and has a friction factor of 0.02. My question is, if you were to place a pressure gauge at the beginning of this 1,500-foot pipe and another gauge at the end of this 1,500-foot pipe, what is the pressure difference throughout the pipe? In other words, what is the pressure drop throughout the pipe? Any ideas on how to start? Usable value, I like that. So what's that usable value?
You need to take Q and then divide it by the area, which is pi over 4 times the diameter, which needs to be in feet.
That is absolutely right. I like how you solve the problem, right? You think of like, what can I use? How do you know that velocity is a usable value, though?
Well, we need pressure, and pressure is directly related to
Oh,
velocity.
perfect, right? So you know that pressure and velocity are directly related, right? So that's a really good idea. Just so that everything is put into context, let me just write down my governing equation here. Here, it seems that the governing equation will be the energy equation, right? Because we're looking for a drop in pressure, which is an energy drop. So I'm going to write down the energy equation, and you'll see that throughout these examples, I'm going to keep writing this equation down, not because I like to waste ink, but because I want to encourage you to write it down so that you memorize it. I don't condone just sitting down reading equations until you memorize them, but I'm okay if you write down an equation so many times that you end up memorizing it because you've used it so much. Remember when we covered the energy equation, I mentioned this was one of the 4 equations in this class that you will actually see in the real world. I don't really like calling it the real world, but I cannot think of any other more appropriate term. This is one of the 4 equations that you actually see in the real world, right? The energy equation. When you talk to some older engineers, like for me, when I talk to my dad and we're talking about this equation, he usually calls it the universal equation because it's an equation that we can apply universally to any pipe system. That doesn't mean that my dad and I sit down and talk about equations. It's more like we're working on a project together and he says, oh, let's use the universal equation. Okay, it's not like, hey, Dad, let's talk about this equation, okay? We have this equation. We can use it. But instead of just, instead of trying to solve every single parameter in this equation, how about we start by figuring out what we don't need and getting rid of it, okay? Do we know this pressure, P1? Do we need it? Yeah, we're looking for the pressure change, right? So we need that pressure. Okay. Do we know this velocity? We can find it. Why isn't that too helpful? Exactly. The diameter is constant, so what happens to these velocity terms? Okay. Try to be nice, use different colors, and it doesn't work. Do we know this elevation? No. Does it matter? No. Okay. Is there a pump in the system? No. Is there a turbine in the system? No. Okay. And that's why I like to do this first. I can reduce my terms. I have P1. I'm going to move this to the other side. So I get P1 minus P2, which is just my pressure drop, over gamma, equals H sub L. But we know that H sub L is my friction loss. And we know that our friction loss can be calculated using the Darcy Weisbach equation. And I think now I have a good idea of what I need to calculate in order to solve this problem. I know that by now you already know how to solve this problem, so don't take it as me treating you like kids. I just want to make sure that everybody's on the same page, right? We need pressure drop. Do we know gamma? What's gamma? 62.4, okay? So I'm going to write it down somewhere, right? Gamma, 62.4. Why do we know that? Where did we get that number? Exactly, that's the standard specific weight of water. Good. We were given the friction factor, 0.02. Do we know the length of the pipe? Yes, 1500. Do we know the diameter of the pipe? Yes, 1.5 inches. When I write down the diameter of the pipe, would I write 1.5 inches here? What would I write? Okay, 1.5 over 12 feet. That's correct. And finally, we get to Trevor's idea, velocity. Trevor said we can find the velocity with the flow rate, right? Velocity equals flow rate over area. My flow rate was 0.1 cubic feet per second. What's the area of this pipe? Yep. Pi over 4 times diameter squared. All right, let's start punching numbers into our calculator. 0.1 over pi over 4. Sorry? Thir- 32 point. Can I get a second opinion?
For velocity?
Yeah.
8.15. That's what I got.
Ah, okay. Tamiya, I'm sorry, I'm going to have to go with the other value, okay? Make sure your conversions are correct. Remember, you divide by 12, then you square. Ah. Good. At this point, is there any more analysis we need to do, or can we just plug and chug? Okay, good. So you can solve it. The pressure drop in this system is going to be equal to how much?
It's supposed to be like a really big number.
I don't know what you get.
Oh, got like 15,000.
15,000, how much?
441.
So 15,400 units. PSF, pounds per square foot. Do you think 15,400 pounds per square foot is a big pressure drop over 1,500 feet of pipes? Maybe if you're not used to dealing with PSF, how about we turn it into PSI, which is something that I think we've all been used to dealing with. So how do you convert PSF to PSI? Divide by 144, right? So how much is this in PSI?
107.
There we go, 107 PSI. It is a pretty strong pressure drop, but over 1,500 feet, it's actually, expected, okay? So good for you for trying to make sense of your results, right? And I think that for these scales, these results are pretty accurate. I know this was an easy exercise, but I did want to make sure that we understand at least how to use the energy equation, so then we can start to look into the details of this fanning friction factor, okay? At this point, are there any questions? Good? Good. Let's talk a little bit about that friction factor. Let's look at it in detail. We don't really have much time to go over the details of laminar flow, other than deriving some equations. But if you do read the lecture notes for internal flows, you may notice that when we are deriving those laminar flow equations, I do start mentioning the friction factor a little bit. And you'll see that for laminar flow, the friction factor is actually only a function of the Reynolds number, which is a dimensionless quantity that gives me the geometry and the velocity of a flow. What that means is that for laminar flows, you may notice that when we derive that equation for Navier-Stokes, that equation, at no point in that equation are we talking about the material of the pipe. But Nash said that friction has to depend on the roughness of that pipe. So when we derived the laminar flow equation, we didn't really consider that. And that's okay, right? Because for laminar flow, we see that friction factor is actually only a function of the flow, not of the material of the pipe. But for turbulent flow, we do need to consider the roughness of that pipe, okay? So in turbulent flow, this fanning friction factor is actually a function of two things, the flow regime and the pipe. The flow regime is represented by the Reynolds number, and the pipe is represented by a property called relative roughness. This Reynolds number, you may recall, can be found by multiplying the velocity times the characteristic length, which will be diameter for pipes, and then dividing by the kinematic viscosity of the fluid. This relative roughness is the ratio of the roughness height and the diameter of the pipe. And this roughness height is actually the average measurement or the average height of those little ridges at the pipe. So in other words, if you're looking at a pipe and you were to zoom in as much as you can, there is no such thing as a smooth pipe. I mean, we can treat it, idealize it as a smooth pipe, but even if you zoom in on PVC, if you zoom in a lot, you're not going to see a horizontal line, you're going to see these little bumps and ridges, right? For any material. Now this roughness height represents the average of the height of these ridges. That's what this roughness height represents. Of course, given that information, do you think how big do you think the roughness height will be for a pipe? And let's say a smooth metal pipe. A really, really small number, right? Because it's so small that we cannot really see it with our eyes, okay? So don't be afraid when you see those impossibly small numbers for roughness height. We're going to be dealing in the orders of like 0.0 something millimeters, so really, really small numbers, okay? Now, for laminar flow, this fanning friction factor can be calculated pretty easily. For turbulent flow, it becomes hard, right? And we're going to have to move from an analytical exercise where we derive equations, solve numbers, into more of an empirical exercise. Has anybody completed their fluids lab yet?
Yeah, I'm working on it right now.
All right. Has anybody done the fluids lab not this semester but in a previous semester? Because this semester is all online, so it's kind of hard to, But there is an experiment in the lab where we look at losses through a pipe, energy losses through a pipe. And in that experiment, we connect 2 pressure meters to a pipe and then run it. We get a flow measurement. We know the pipe diameter. And then we get these pressure measurements. And the reason we do that is because if we look at the pipe, horizontal pipe, constant diameter, we get the same equation, delta P over gamma equals FL over D, V squared over 2G. And when we're doing the experiment, notice that if we can measure these 2 pressures, we have delta P. We know that our fluid is water, we have gamma. We can measure the length, we can measure the diameter, we can measure the velocity, so what's left? The friction factor, right? So we do that experiment in order to find the friction factor for this pipe. Now the reason we do that is because there is no analytical way of saying, hey, this is my friction factor, here's the equation that proves it. Instead, we resort to these empirical or experimental methods to determine the friction factor. Now I like that experiment because it's actually a pretty practical one. However, somebody else already beat us to it. A man by the name of Dwight Moody. Hang on, let me make sure I have the name right. I follow 2 Moodys. I read about this Moody that deals with fluid mechanics. Then I also read about another Moody that's a Christian guy. What?
Is it Lewis Moody? That's what it says in the note.
L.F. Moody, Lewis Moody. Okay, scratch that, not Dwight Moody. A guy by the name of Lewis Moody actually beat us to it and calculated these friction factors for a number of Reynolds numbers and relative roughnesses so that we wouldn't have to. And we see that in the Moody diagram, which I guess I should probably project here. What Moody did was he measured different values of Reynolds number, relative roughnesses, and then their resulting friction factors, right? So he looked at Reynolds numbers, relative roughnesses, and then friction factors, and then combined these values into a conveniently placed graph, okay? And how does this help us? Well, using Moody's diagram, which is pretty much the industry standard, using Moody's diagram, if I know the Reynolds number for my flow, and I know the relative roughness for my flow, then I can determine or estimate the friction factor. Now, using it takes a little bit of work. What's important is these lines that you see here, these curved lines, represent equal or represent similar relative roughnesses. In other words, this line where the relative roughness is 0.0001, throughout this line, the relative roughness will still be 0.0001, okay? So why are they curved? Because the Reynolds number, right, will then tell us where the Reynolds number intersects with that line. That is the friction factor that we're going to use. And we're going to do some examples, so don't worry, I'm not going to just say this and throw you to the wolves here. But essentially, if you know your relative roughness and you know your Reynolds number, you can move following your relative roughness line until you have an intersection with your Reynolds number. And from there, it's a straight shot to the left and you get your friction factor, okay? So let's try a couple of exercises just to make sure that we actually know how to use this Moody's diagram, okay? How about we try this example again? But let's say, right, we're going to have a similar setup. Let's say that we don't know our friction factor. And because the fluid is water, the kinematic viscosity is 1 times 10 to the negative 5 feet squared per second. You may want to memorize that number, right? 1 times 10 to the negative 5 feet squared per second. So given that information, right, we know that the kinematic viscosity is 1 times 10 to the power negative 5 feet squared per second. And let's say that this pipe is made of a material whose roughness height is 0.00015 feet. Okay, so we have a little bit of new information. Let me clean the board a little bit so that we don't have so much stuff in there, but we have flow rate. This time we don't know the friction factor, but we know the kinematic viscosity of the water, and we know the roughness height. And we would like to use that to find the pressure drop again. We have the same equation. We don't have to come up with the equation again. We know that the pressure drop over gamma equals the friction losses, which can be calculated using Darcy-Weisbeck equation. But now, let me say, we want to find pressure drop. Do we still know gamma with the changes we made? Okay. Do we know friction factor with the changes we made? No, but we can calculate, right? And then everything else remains the same, okay? So let's recall that velocity was, is it 8.55, 8.15?
8.15.
15, okay. So we do have that velocity, that doesn't change. But now let's find that friction factor. Now, in order to find the friction factor, we need to recognize that the friction factor is a function of the Reynolds number and the relative roughness. Therefore, we need to find the Reynolds number. The Reynolds number we know is a dimensionless number calculated by taking the product of velocity and diameter and then dividing by the kinematic viscosity. In this case, my velocity is 8.15 feet per second. My diameter is 1.5?
Yes.
Divided by 12 feet, that's correct. And then my kinematic viscosity is 1 times 10 to the negative 5 feet squared per second. Feet squared, second. Yep, everything cancels out. And this gives me a Reynolds number of how much?
101,859.
Let's just do it in stick fix. So 101,800, so 1.02 times 10 to the 5?
Yeah.
Okay, good. Units? None. Dimensionless, right? That's correct. Sorry?
2 works as well.
Rounds. Oh, sorry. Yeah, no, sorry, it's 2. No. No,
Okay.
no.
Let's calculate the relative roughness. Relative roughness is simply the ratio of roughness height, which is given to us, 0.0015 feet, or 0.00015 feet, and then the diameter, which is 1.5 over 12 feet. A couple of notes. Normally, no one's going to say, hey, here's the pipe, here's the relative roughness. In industry, that's usually the value you have to look up. So for example, when I deal with pipes, I kind of know now because I've dealt with them so much, but no one's going to say, hey, here's the pipe, here's the relative roughness. It's more of a value that I have to look up. And because that relative roughness gives you the roughness of the pipe, it should be obvious, if it isn't already, that the newer pipes should be smoother, but then as you use the pipes, they become rougher. So you also have to apply a little bit of engineering judgment there, saying, hey, how old is this pipe? How long has it been used? At what velocities has it been used? And you can use that to kind of estimate your relative roughness. Yep.
You said they become rougher the more
They do become rougher. You may think it's the opposite, right? You think, oh, wait, when you use them more, it actually erodes away those ridges. It's actually not that way. When you use them more, it actually scours. Well, scour is not really the correct word, but it actually like makes the ridges even
Is that
worse.
because the flow is not, like if you assume perfect flow, is that why?
The flow is turbulent, not laminar, right? So we're dealing with laminar flow, turbulent flow, where fluid particles are just moving everywhere. And you see that. You may see, is anybody here studying civil? Yeah. Poor guys. If you ever do a trip to a stormwater management or stormwater system, like maybe a pipe or something, ask if you can like step into that pipe. I mean, be careful, but ask if you can step into the pipe and look at it. And you'll see that at the bottom where there's more water flowing at the bottom of the pipe, it's actually rougher than at the top. And everything looks kind of smooth at the top if the pipe is not full. But then at the bottom where water actually flows all the time, it actually becomes very rough. So, I mean, it's not like it's fun or anything, but if you can, try to like, touch the top of the pipe, touch the bottom of the pipe, and you'll see the bottom is rougher because there is more water traveling through it, okay? And then for the rest of you that picked a good career, then you don't have to do it because you're mechanical engineers, okay? So we find the relative roughness. What does that equal to? Good. Units? None, right? Dimensionless as well. So we can use this to now calculate or maybe calculate is not the right word, estimate or determine the Reynolds number. And for that, we turn to the Moody diagram. The Moody diagram relates the Reynolds number and the relative roughness to the friction factor. So how does that work? I want to start with my relative roughness. I have a relative roughness of 0.0012. So I'm going to look over here at the closest number to 0.0012, right? So if I look at this diagram, notice that I have 0.001, and a little bit higher than that is 0.0012. Is that correct? Because higher, we have 0.002. That's already too high. So my 0.0012 lies about 2/10 of the way, right, between this number and this number. You may notice that I've already used this example before in my class because I actually marked it so I wouldn't forget. But essentially 0.0012 should lie somewhere in between 0.001 and 0.002, right? But then once we know where that number lies, we just have to follow this curve. In this case, the line is actually gray. It's a little bit harder to see on the board, but you follow this curve until you intersect with the Reynolds number. For the Reynolds number, we got 1.0 something to the power of times 10 to the power of 5. So we look at, and here you want to be careful, this is 1 times 10 to the power of 3, 2 times 10 to the power of 3. Okay, so it's not like 10 to the power of 3 ends here and then we start to, no. This is 1 times 10 to the power of 3, so 1,000, 2,000, blah, 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 10,000, okay? So if we're looking at 1.02 times 10 to the power of 5, we start at 10 to the power of 5, and this is 1 times 10 to the power of 5. So 1.02 is actually going to be pretty much almost at 1, basically, right? 1.02 is pretty much almost at 10 to the power of 5 because they're really, really close. We essentially want the point where this gray curve, or a line a little bit above this gray curve, intersects with this number, this Reynolds number, right? And that point following that curve of the line is going to be somewhere up here. And if you do a straight shot to the left, you're going to get a friction factor somewhere in between these two lines. I know it's kind of hard to see with my fat fingers, but essentially, once you do have your pens and your pencils, you can actually try to fine-tune it, right, in order to get an appropriate friction factor. The friction factor that I got by kind of estimating, right, estimating from here, finding the intersection point, and then straight shot to the left, was about 0.023. That's about what I got. So 0.023, somewhere around here, okay? That was the friction factor.
You follow that gray line, the curved gray line that starts around your mark over there? Mm-hmm. Okay. I was making sure.
And you follow that curve,
okay,
right?
Staying your original distance off, right?
Yeah, or a proportional, because notice that as you curve more, your distance becomes closer. So it's actually staying a proportional distance away. So if you're at 2/10 of the way between the gray line and the black line, you got to be at 2/10 of the way between the gray line and the black line, which may be a shorter distance. Yes?
There's a way to view an interpolation calculator on Excel.
We're going to get to that. There's actually several equations that kind of interpolate this, right, for you. So yeah. Now, because we don't have too much time, let's just go ahead and try to finish this problem, right? We estimate a friction factor of around 0.023. But then from here, all we have to do is insert that friction factor there. So if we do that, we get that the pressure drop is going to be gamma, which is 62.4. I'm going to forget the units because we're running out of time. times friction factor, which we estimate at 0.023, times length over diameter, times velocity squared over 2 times gravitational acceleration. And what is that pressure drop equal to? Well, it can be the same because I had a different friction factor. I just want to know what the difference is out of curiosity. Because we only have a difference of 0.003, right? So what's that pressure equal to? Pressure drop.
Got it. 17,763.
How much is that in PSI divided by 144?
123.36.
Okay. Earlier we had 107 PSI, right? So only a 0.003 difference in the friction factor results in about 15 PSI difference in pressure. 15 PSI is not a small number of pressure, right? Yeah, the tires in your car have pressures of 30 already. So it is a sizable difference compared to the small amount of difference in friction factor, okay? Let's leave it there. Go ahead.
I just had a quick question on how roughness type is, like, how is that measured in like a workplace situation? Or is that like,
Ask the manufacturers. So the manufacturer typically, based on the material, they measure that value. And that's with very, very precise. And they don't measure it for the entire pipe, right? It's more like, hey, this is concrete. Concrete on average has these ridges. This is steel. Steel on average has these ridges.
I didn't know if it was like a cross section and then like a microscope or like how exactly they measure that.
Yeah.
A laser scanner.
All right. I'll see you next week.